programming with SIG. We actually don't have a specific task today. We're going to be continuing with where we left off from yesterday in regards to the Tetris game we are currently working on. So, the Tetris game currently, we're drawing a board that selects a piece at random and then drops that piece and then renders the next piece, so on and so forth. One thing we established is that the position of the player's, the player position is located right in the center, and then everything's kind of drawn around that center. So we can see here we established the center to be in between these, and so the player position is at 5, right? So everything to the left of 5 is this way, and then everything to the right of 5 gets right that way. So if you split all the pieces in half, approximately you'll end up with something kind of like that. So today we're first going to be working on rotations. And then we're going to be working on allowing the player to move their piece around the board. And finally, we're going to be working on line clearing and then implementation of the actual game rules, which are every, I think, 10 lines you get a level up or something like that. And then we can add in scoring and stuff like that today as well. In order to make rotations happen, we actually have a place where rotations are already happening. So reviewing our code, we actually store what shape we're currently using inside of the player. So I'm going to pull up the player object real quick. So you can see here, piece stores the current piece. Now the piece is based on one of these shapes, and so the current piece selected, you see we use rotation to determine which shape from that piece we're currently on. So simply by changing the rotation variable, we will end up rotating the piece in a different direction. So that's easy enough. Rotate the piece one way, rotate the piece another way. Those are two functions that we will need. So we'll say rotate clockwise and rotate counterclockwise. Now, because this is a looping value, as in once it hits 0, it's going to loop back to the max value, and once it hits the max value, it's going to rotate back to 0. We're actually going to use modulus here and if statements to solve that. So for example, with this piece, when we want to rotate clockwise, it turns into this shape. So rotating clockwise will increment the rotation variable by 1. However, we can't just rotate it. When we rotate a piece, we have to check if all the new positions of that piece are empty. And if they are not empty, then we have to actually try to move the piece. So I was thinking about this, right? If the piece doesn't fit when you rotate it, then you need to try shifting it either one to the left or one to the right. Why only one? Because, well, we can't have the piece be teleporting everywhere. So we can try moving one to the left and one to the right. If we can't, then we reject the rotation. But we try to rotate the piece to the best of our ability. So, the rules of rotation are get the new rotate piece, see if the current piece position with the new rotation shape overlaps any active squares. If they do, try to shift the piece one left and compare again. If they still do, try to shift the piece one right and compare again. If no piece position is free, we cannot rotate. Return. Otherwise, all conditions have been met, and we can rotate the piece. And we'll be doing the same thing counterclockwise, so we're actually going to have a rotate piece value, and we're just going to choose like a direction. So really, it's going to look like this. when we confirm which piece we're rotating. We're going to have rotate piece direction, and we'll just change the variable directly by saying game.rotation plus equals direction. If the variable is less than 0, set the rotation equal to 3, which is the max value. Otherwise, if the rotation is greater than 3, set it to 0. I did say we were going to use modulus, but we can accomplish it this way as well without many problems. So these two kind of follow like the same, they're both going to call rotate piece, just in different directions. One's going to increment and one's going to decrement. But inside of these structures, before we can rotate the piece, we have to determine the piece locations. So we kind of did this yesterday by using these checkpoints here. So we can determine what locations are occupying the current player block by using this function we made from yesterday. So you can see all the refactoring and functionality is starting to come into play here. This is a local call to get player blocks in grid. So this returns all the points where there is a player block within the grid system. So with that in mind, we're just going to compare them to the actual grid and see if any of them are active. But we have to first translate it. Now the nice thing about this is all these points can be translated. So just like we do down here when we're checking if the next position is occupied, we'll basically use the same function. Now you'll notice we're going to be copy pasting this function. So all of a sudden we're thinking, since we need something that returns whether it's occupied, we can make something out of that. However, I will point out that right now, this is also offsetting by 1. So it's doing something a little like unintuitive in a sense, because right here, this point.translate also shifts it down by 1, I believe. Let me double check that. You know, I don't actually see the shift down by 1. Oh wait, it's right here. -1, -1. We see that, right? So we're going to have to specify an offset here, because sometimes the offset is going to be different depending on what we're looking for. So we're going to need some parameters called offset. So we're going to add some parameters. The refactoring tool isn't smart enough to detect that sometimes, but we're going to be making a function kind of like that. We're going to call it is occupied. So simple enough. It checks if all the points provided are if any of those are occupied. That's what it's going to do. But we're going to provide a offset here, and by default we'll say the offset, or I don't think you can specify default arguments in Java. Yeah, I'm pretty sure you cannot. However, you can specify a version of the function that can give a default. So this is just going to call is occupied, where the offset is 0, 0. Thereby making a way to have like a default in a sense, and return that. So this is going to call this, but with 0, 0 here, if we choose to use that version. However, if we provide an offset, then we're going to check the positions using that offset. Offset.y here. And we're going to go, should we go negative? I think we should go, yeah, we're going to specify negative offsets if we want to go down, so that we're oriented the correct way. So now we need to refactor this a little bit, because the offset we're checking for is actually at 0, -1. But now we can use this function to see if it's occupied over here. So combining both this, where'd it go? Where am I? Combining both this And this function here, it's actually stored in game right now. And make sure it's public so it's actually visible. Now we can determine if any of these points are occupied by the new blocks. So we're going to keep the offset at 0, 0 here because the block's not moving. We're just trying to rotate the piece. But this right here, you can see we're not trying to check the current block. We're trying to check a rotated version of the block. So this now needs a shape argument instead. So we're going to kind of extract that from here. So we're now going to force us to give a shape. And the shape can be, by default, it will be like this right here. But it can be anything. And we're trying to make this generic, so we're now going to have to update all the places where this is referenced to use the correct shape. So in this case, we just specified the player's piece shape here, but and we're going to provide a different rotation. So here we just update rotation directly, right? But we can make it so we update a rotation given. So we can provide like the current rotation and the direction and return a new rotation. Thus, when we say rotate clockwise or rotate counterclockwise, we're actually going to set game rotation equal to a value we specify there. And this way, now it's more flexible because we're rotating not just the value of this, but we can specify a rotation when we're referencing it somewhere else. And this makes for cleaner code because now we can use rotate piece elsewhere. And in this case, we gotta actually return rotation. So we're gonna modify current rotation directly and then return a value. But it's a primitive, so it's not gonna affect what's called in. It's just gonna affect what goes out. So current rotation plus basically all these get replaced with that. Game.rotation replaced with current rotation. Like so. So now it's more generic. You can see how if you make your functions more generic, you can use them in more places. They suddenly become more useful by doing all this like refactoring. So you can see how we've used isOccupied now in 2 places in our code. We're now using getPlayerBlocks and grid in 3 places in our code. We refactored it even more generically so that we can provide any shape, because we're about to use it down here for a different rotation shape where we say, so instead of the current rotation, we're now going to say rotate clockwise. Wait, hold on. We're already in rotate clockwise, so it's like we're calling rotate piece from the current rotation plus 1. So you can see how we can use rotate piece to get a temporary value of what our new rotation is going to be before we actually rotate the piece, which we would do down here. So this suddenly makes it a much more useful function because we can use it in more places and do the same function that we would have to copy and paste everywhere. Like, why would you copy and paste functionality that you need to do everywhere at once? And this is something about object-oriented programming that takes a very long time to grasp. You don't realize, oh, I need to use this in multiple places. So how do I make this function generic enough to where it is useful in more places? And again, that's why on day 1, we broke down functions into multiple tinier pieces. Because as you break functions into tinier and tinier pieces, you suddenly realize that you can use all these tinier pieces to then construct bigger pieces again by making effectively useful functions. Refactoring reveals what the true identity of your code actually is by seeing, oh, this could be made more generic. It doesn't just update game.rotation, it can update any rotation, which then is modified through different calls. Anyways, in here we are referencing the player's shape. Not the next piece, please, the current piece. And we're gonna provide game.rotation there. So you can see this right here is a little annoying to write as well. So it might be better to make something to simplify this by saying return get current shape. And so we can then return piece.shape game.rotation. And that makes it easier for us because now we can call this instead of this mess every time, which makes it a lot easier to understand for us. And I believe that is... oh, there's one more location to fix this in, and it's up here. So we will do that. Okay, now, before we go any further and talk more about this rotate function, we're going to make sure that our code still functions the way it did before. As we can see, it is still creating the falling block, and so none of our code has broken. So every time you make changes, you probably want to make sure that everything is still working the way it is. We're not doing test-driven development for this kind of stuff, but it's something we can consider doing in the future. Test-driven development is a lot more time-consuming, and so, but it's highly recommended. It's worth it. So we're definitely gonna get into it at some point, so we can become better at it and get faster. But in the meantime, at least we need to make sure what we currently got is working properly. Anyways, let's get our rotate functions working now that we've done some refactoring and our code is a lot easier to work with here. So we're gonna grab the blocks in the grid that are occupied by a rotated version of our current shape, which we're now able to do because of all these changes. So we can even refactor this part further if we wanted to say get a clockwise rotated piece. Get clockwise rotated piece. Current piece. Like, we can actually write that if we wanted to make this a little easier to understand. And thus we can do kind of the opposite, get counterclockwise rotated game piece, which would just be a -1 there. And that way we're getting all the player blocks in the grid using the clockwise rotated current piece. A little easier to understand that way, I guess, than the mess we had in here. So if found occupied spot, I guess I'll call it that. If found occupied spot, then what did we say we're gonna do in the logic? Well, we're gonna try to shift it one left or one right and try those locations again. So, interestingly enough, checkpoints are the current locations, so we just need to shift all those points one left or one right. There's a couple ways to go about doing that. We could just take all the points inside of here and modify them, and then check again using this, or not this, this. So that's one way to do it. The other way is to generate a whole new set of points with these all offset, which is also possible. But yeah, we already have an offset here. We're not implementing the X though, so we need to actually do that. So let's make use of the X offset now for is occupied. So in order to do that, we just need to modify this to say plus offset.x. Now we need to do some bound checking, because imagine if we checked a position like at -1x or 1 off of the max length of x, and same with the y's. If we go off this grid, we're gonna get an error, right? We actually saw this yesterday when we were running this code, and we had the board top out. When the last block hit the top, there were blocks or pieces of a block that were on top of the grid, and because of that, the program terminated with an error. So we have to actually do boundary checking. We kind of did it with this, but we need to do more checks. So before we can do basically you have to do the boundary checks before you do the array check, because you need your logic to terminate before you reach the array check. So everything that can stop the check earlier needs to be in front of it. That's just how logic works. If you have a bunch of OR statements, once any condition is met in an OR logic loop, then the computer doesn't have to run the rest of the logic because it knows, oh, well, if one of these is true, then it does this. So you don't have to worry about this ever executing if you can stop it beforehand, which is what we're going to do here. So we're going to see, we already checked if point.y plus offset.y is less than 0. Now we have to check if it's greater than the edge of the array. So GameGrid.grid. We actually already know the height, so we could technically use the height. But usually what I also like to do is just grab the first element and then do dot length. So that's another way to do it. Either way, you're gonna have to grab that somehow. Moving on, we need to also do the same boundary checks before the X. So each element in grid is the X. So by doing this, we can get the X length, the maximum X can be. And then we'll also see if this plus this is less than 0. So if any of these conditions are met, we're going to say yes, that square is quote-unquote occupied. It's just outside the boundaries, so it's considered occupied, and thus it leads to solid collision checks, like here, for example, which prevents us from moving. So if we found an occupied spot, then we're going to continue. We're going to try game.isOccupied, Boolean secondary check. See if one position to the right is occupied. If secondary check, we can actually just do this. These if statements can be directly imported. I don't really find the names to be super useful, so we're actually going to replace it with that. So if this is true, then we're going to try this, and if that is true, or this is true, right? So basically, our logic ends up being, if this is true, if this is occupied, and it's occupied here, and it's occupied here, then we're done, right? But we need to add some logic to say, after you try a position, then we try a different offset, and then you try another different offset. So we basically need to determine which offset is free. Because let's say, for example, this position is free, but this one was not. It's gonna do this, say nope, and then it's gonna do this and say, yep, it's this one. But how do we know that this was the one that passed for the test? If we're checking all of it in one loop, we can't track that. We can't possibly know which one of these passed unless we track it ourselves. So in order to fix this, we're gonna check different offsets by storing them all in an array first of all, and by storing them all, oh gosh, syntax. By storing them all into an array, what we're going to do is, depending on which offset returns okay, we're going to return that value for use. So int free offset equals I is less than offset.length, I plus plus, go through each offset. Then replace, I don't know why I did y, by the way, I'm glad I caught that, but we're trying to offset x, not y. So, oops. Anyways, we're seeing if any of those are occupied. Wait, what? Oh, right. Offset I, make sure we get the index within I, or offset. And so if it is, we're gonna return free offset is equal to offset I, and just break out of this loop. We don't have to keep checking stuff. Now this is great and all, however, we can refactor this a little because it looks a little messy, right? It's not clear what we're doing here. So we're gonna just name this get free point. Now it's not returning an integer, which is kind of annoying. So we need to actually make use of that integer. So if free, I guess we'll say -1 here. So if free offset is not equal to -1, then we have clearance to rotate the piece. So now we can refactor all this and get what we want. So we could say, try to rotate piece. That's not quite what I want because I still want the rotate piece to be... Rotate pieces based on the offset, I guess. Temp to rotate piece. We'll do that. Actually, let me refactor that. I know what I want to call this now. I want to call this, how do I refactor? I'll shift R. I want to say, rotate if space is free. There we go. That's what I want. So this function takes in any like rotation and says, okay, try to rotate it. If we can rotate it, we'll do it. Now, if free offset is set to something else, like for example, we shifted it over, we have to actually move the position of the player over as well. So pause.translate to free offset 0. And this is just to make sure the player moves with the block. We don't just say, oh, we can move to this location and then don't move them. Then we're gonna have overlapping blocks. So we have to make sure the collision check is good. Now, the interesting thing is, all we're left with is copy pasting this into rotate counterclockwise. We actually don't even need this part anymore. Interestingly enough, the only thing we didn't specify is a rotate piece argument there. So we're gonna specify that actually. And you might also notice that both of these need that same number. Like for example, if I type in counterclockwise here, and then I'm gonna be typing a -1, well, -1 is also needed here. So seeing two arguments that are the same, and thus if I type up here, I'm gonna be putting a (1) because I'm gonna be satisfying this argument where I say get player block is in grid, but the rotation, wait, am I doing this right? Rotate space is free. I think I'm doing this in the wrong place. Yeah, my bad. Down here is where I'm trying to say that. So here we can specify rotate space free and the direction of the rotation as an argument. So in this case, -1 for counterclockwise and 1 for clockwise. If we want to make it more clear which number was which, we can also make another enum. So enums are good for naming direction, and we can specify, let's make this a little more specific actually. We'll call this the rotation direction, right? And we have clockwise and counterclockwise. Now by default, both of these values are just set up by the compiler itself. They'll usually be set like in order, so like 0 and 1. But we can also specify like a value for them to represent by specifying arguments. So if I provide a 1 and a -1 here, now we have to specify a constructor for this rotation direction, and then we specify like an integer that says we'll call it the value. And then we'll need to store that somewhere. So these will need a local value. So this dot value is value. And then when we actually grab these, we're looking at these values, not necessarily these numbers here. So we'll pass in the enum, so rotation direction dot counterclockwise. And we'll also pass in rotation direction dot clockwise up here. And you'll notice we can do this in a couple places because we now have ones and zeros down here as well. So here's clockwise, counterclockwise, and clockwise. However, we're going to be replacing this with our argument. So this is going to become a rotation direction, and we'll just specify dir.value here to get which value of direction we're actually rotating as a number. So this still passes off as proper. So clockwise rotate current piece is going to be this dot value, and we can actually change this to require a rotation direction. And that way we can even break this down even further to not even require the value, it just requires a direction, and then we just do it all down here. You want to try to break down your abstraction at the lowest possible level. So for example, what I just did here, let me change the value, that's exactly what I did. Plus equals direction dot value. Did I not save? I did not save, my bad. But what I mean by that is you see how we used rotation direction in these two functions, both in rotate piece and rotate if space is free. And both of these, all of these call rotate piece here. So if you break it down here, you would have to put dir.value, rotation direction.clockwise value, and rotation direction.counterclockwise value. But why put value here and break down the abstraction there when you can break the abstraction down at the lowest possible level? So doing it in the rotate piece function makes the most sense because now you're abstracting at the very, very end. So with all this now in place, you can see our rotate clockwise and our rotate counterclockwise functions are both just 2 lines of code thanks to all of this abstraction here. So we turned all of this into 2 lines of code, which is very nice for us because it makes it very easy to understand what is going on. I mean, yeah, we can look in here and say, okay, we're checking if things are occupied based on an offset, but if we're just looking at this, we're saying, okay, get the player blocks in a grid, get the rotated version of the piece, see if the space is free when rotated, and thus move it. That all can be translated into this big function here, but looking at this, we get a very easy way of identifying what's going on. So now we have to test if they actually work, right? We're not sure if they work yet. So what we're going to do is we're going to make it so whatever block is created and it starts falling, it's going to rotate clockwise every, I don't know, every few ticks. We'll make it rotate. The game will rotate for us because we don't have any user input yet. We're not going to worry about user input quite yet. Because we don't have all the game logic in yet. So let's get all the game logic in first before we worry about user input. But we'll make some new timers here. Let's say rotate delay is going to be 20, and the rotate timer will be equal to rotate delay at first, and then it'll count down as it gets closer to 0. So we will now specify those values inside of our step event, as I'm calling it now. We're in the wrong class, actually. Let's go back to game. That's where I moved. So we have move block here. So after we call, this just plots our stuff. So we're gonna call move block, right? If rotate timer is less than or equal to 0, we're gonna actually rotate the block. So we'll do p dot rotate. We'll do clockwise first. We'll test clockwise, and then we'll say rotate timer equals rotate delay. So what this is gonna do is every, I think 1/3 of a second, it's gonna do a rotation. In theory, it didn't actually set the piece, did it? We kind of forgot about that part. We did all this rotation checking, but we didn't actually rotate the piece. So let's do what we say and actually rotate the piece now. So game.rotation equals rotate piece. This should return whatever the value should be. So let's see the before and after here. Make sure we're returning what we're supposed to. It could also be our timer does initialize. Yeah, I'm not seeing any output, so I don't think our timer works. And that might be because I forgot to decrement it. Yep, I forgot to decrement it. So let's decrement our timer. My bad. Alright, so out of bounds exception 4. Now that's kind of interesting, because I could have sworn we actually checked, let's see. So it's trying to add more than 4 blocks? That's weird. Because there's only 4 no matter what shape you give it, as far as I know. There's no block out there that has 5 O's? Oh, there's one. Actually, one. How did I manage that? Oops. Let's fix that. Yeah, these all have 5. That's wrong. Let me figure out to fix this. I think what we're gonna do is move this over. So that's my bad. I didn't catch this earlier. Oh my gosh, I'm making it worse. So I need to fix my pieces so that they're not gigantic, monstrous sized pieces. Like so. And then this one, we had the same thing happen. So we're gonna fix that. Alright, that piece looks good. That looks fine. That looks fine. Okay. Yeah, all the other pieces look like they are all 4 blocks. So that's a good check. We make sure we limit it to only 4 blocks. So it's supposed to be rotating every once in a while, but it's not. So, I think what is happening is... Let me see. So we do lower the rotate timer, and when it's, let's say, equal to 0, we're going to rotate clockwise. So let's make sure this is being called first, and then we'll go from there. Rotation. Let's see if anything is changing in there. Array index out of bounds exception. Wow, right away? Really? Ah, we didn't do our boundary check right. We need to do greater than or equal to here because it can't be the length. It has to be 1 less than the length. So I don't see anything being outputted. Although it's hard to say because we don't really have a proper... let us make it so this doesn't output for now. The board itself. So all of this is to output the board. Including the clear screen. So draw board. Draw board function. Later on we'll actually turn that into a graphical user interface thing, but that way we can easily comment it out and just look at the raw stuff. So we see that nothing's being output to the console, so it's not actually running, which tells us that we got something to look at here. I don't know when I started, by the way. When did I start? We're currently 40 minutes in. Wow, that's pretty fast actually. In any case, this doesn't output rotation, so that means that free offset probably didn't get set here because we're checking if it's occupied. So I think the logic here is reversed because we're seeing if it's not occupied. Because if it's not occupied, then we have to rotate, right? So this is reverse logic from what we actually want. So we can see now it's rotating with 0, 1, 2, 3. So now we fix that with the reverse logic issue. We can draw our board again, and we can remove the debug message here and take a look. So you can see here this piece is being rotated clockwise as it falls. So we can see that that logic is indeed working the way it should. I'm just trying to make sure it's actually rotating clockwise and not just rotating at random, and it looks like it is doing that. Now you'll notice that the collision actually tries to work itself out as well, so that's kind of cool. But yeah, that is rotating clockwise indeed. And it tries to rotate around other pieces and such if it can. We can't really test the like one block to the right or left part until we implement further. And also we added some boundary checks, so this technically will go on forever. There will be no like lose condition. The blocks will just, oh, it eventually fails actually. I'm not 100% sure. Oh, I see. It's because we try to set all the blocks, including the one up here. And that's some separate logic. That is done in move block, I believe. So yeah, we can see here, if it's occupied, try to set every point in the grid. But again, you can see we need to do a boundary check, because if the grid is outside, then actually that's our lose condition right there. We need to make note of that. If any point in the grid is outside, this is our lose condition, and we lose. So we can actually make an easy way for us to detect a loss now by saying, okay, if any of our blocks reach the topmost part of the grid, then we lose. So trying to think how I want to control this. Usually when it comes to game like win conditions, you have like a state machine. So we can make a new enum called game state for something like that. So you have a couple of game states, and we'll probably set this up later. You're either playing the game, you are you won, or you lost. Those are our only game states right now. You might add game states like a menu, an options menu, what have you, a level select, right? That might be a good idea to have in the future. But for now, as a basic idea, we want those enums that we can reference. So, with those game states in mind, we're gonna say if point.x is, if point.y is greater than or equal to whatever the boundary is. We want to try to keep it flexible, because you never know if we decide we want to make the boundary of the game bigger, then we want to have that flexibility. So if it's greater than or equal to the length of this, then we can't attach it to the grid. That would cause an error. So our grid length is 20. So when y is at position 20, we know we lost. So we're going to set the game state. We don't actually store the game state anywhere, so let's store the game state real quick. Game state. And we'll set it to playing originally, because that is what we're doing. We're playing. So down here, we'll change the state. Game state dot lose. So that's our lose state. I don't know if there's really a win state. You really just play Tetris until you lose, don't you? There isn't really a win. I mean, there could be a win if you clear certain X amount of things or something, if you have like a mission. But by default, I think regular Tetris is just never ending. So there's that. Anyways, our rotation function works. We can check if our counterclockwise rotation works, but I'm pretty confident it does, since, like, if I were to copy and paste code, I wouldn't be so certain. But I know that because we implemented it so tightly, and we have just one function calling which direction to rotate it, that both of these would work, because it's just literally a change in this value. So that has very little room to go wrong, because every other part of the code is exactly the same and all shared with all these methods. So I'm pretty confident that we don't have to actually test counterclockwise, because I know for a fact that it's going to be pretty much the same thing. Apparently I made this a lowercase. I kind of don't like that. I'm going to refactor it real quick. Okay. I instinctively typed it with an uppercase, but it didn't quite work. So obviously if you try to rotate an O block, it kind of keeps its shape. It doesn't rotate. So counterclockwise, we can see it's going the other way now. You know what's weird? I think I got clockwise and counterclockwise backwards. I could be wrong. Oh, you actually saw it shifted over here. So our shifting over code does indeed work for trying to move the block if it can fit. So that's pretty nice to see. That just keeps things smooth when it comes time to actually rotate blocks. The user isn't frustrated because their block will slightly fit to one side or the other and they just can't push it with one rotation. So that's why I added that little wiggle room. We just don't want it to be too much, because then blocks will be teleporting everywhere and that will look weird. So we got the rotation functionality down. The next thing is to make the line clear functionality. Now the line clear functionality is pretty easy, because we just have to check if any rows are all active. So that happens every time a piece snaps, right? Because then the grid state changes. So every time the grid state changes is when we want to check if the line is cleared, if the lines are cleared or not. So right after, let me see. Go back to our game logic. So we have move block, which determines if we get stuck. So this is a good point to refactor a little, because I can't at a glance see, okay, this is what happens when the piece... So this is all the logic that happens when we do a piece snap. So we're going to call this piece snap. That way we understand, okay. I'm actually going to change this a little. I'm going to flip the verb and the noun. Snap piece collision. Snap piece that collided. Yeah, okay, that's a little more descriptive. Because when I look at this, I can't immediately understand, oh, this logic refers to a piece touching something. So now that I know it's here, I can say, alright. And I'm going to actually change this too, because this isn't really clear either. So we're going to call this move player block down by 1. Now the thing about refactoring, you'll notice my function names are starting to get pretty long. The more detailed you get, the longer your function names generally are, because they become more and more specific in functionality, right? You can see here, my function names are pretty long too. Rotate if space is free. Get clockwise, rotate current piece. Clockwise, counterclockwise, rotate current piece. Rotate counterclockwise was inside of rotate if space is free. Same with rotate clockwise, get current shape. You can see as we get more generic, the function names tend to get smaller. And that's because, you see, move block is smaller than either of these. And then move block is inside of step. So naturally, and step is inside of run, like this is just a natural progression where the more detailed you get, the longer your function names generally get, because now you're doing more and more specific behaviors. So when we snap a piece, we're going to be check board for line clears. Or we can call this clear lines that have full rows. I think that's a good name for it too. Right now I can't think of any arguments this would need because the grid is already defined inside a global. So we're just going to have to check every grid. So we're going to go through all rows. So we'll do game grid dot length. So this will get each row, I believe. Let me think. Rows are... Yeah, rows are 10 in length each. Why does this not work? Oh, wait. Dot grid. Game grid dot grid dot length. Okay. So for each row, we're going to see if all the elements inside that row are active. So the way you check for if everything's active is by marking something to say is all active, is true. And then if any of them are not active, then you flip that to false, and then you exit the current loop you're in, because you don't have to check the rest if one is inactive, right? Game grid I dot length J++. And if we want to be a little more specific, we can actually change this to represent the X. This represents the rows. This represents the columns, the Ys. So by putting in X and Y, it's a little more easier to visualize because it is a Cartesian coordinate system. So it's better to visualize that with X's and Y's instead. So if any of these values, grid X, Y dot active, we're seeing if it's not active, or yeah, if it's not active, then is all active becomes false, and we can immediately break out of this for loop. So we're done in this for loop. So right here, we can now refactor this to say, check if all are, well, we're not using is all active yet. Once we use is all active, then we'll refactor it. So if is all active, we have a line clear. So with a line clear, what is the logic? The logic is going to be, first, all the blocks above the line you just cleared shift down by 1. That's how it works in Tetris, right? When you get a line clear, every block above shifts down by 1. So you basically pop off whatever row you're on, and everything above moves down. So take every... We're just going to write this in words. Take every block above this row and shift it all down by 1. Okay. That's not too bad. We're probably going to turn this into a refactored function, but we're going to have to iterate through every grid value above us to figure that out. So, starting at a certain Y position, so we're going to store... starting at a certain X position, we already know what X is. X is the current row we are on. So every row above us needs to come down by 1. And I would say, now most of the time when we think of clearing a line, we're thinking, okay, we need to delete the line we're currently on. But if you think about it, if you just shift every row above you down by 1, that will automatically remove the line you have, as long as you do a replacement. For example, if you don't replace every block, including inactives, then what you're going to end up having is everything's just cleared again. So you have to make sure you do an actual replacement and make all active blocks inactive that are inactive above it. So to iterate through every single row that is above us, we kind of have to start from the row we're currently on and work our way backwards. So we'll say int row is going to be equal to x, because x is our current row we're starting on, minus 1. And then we're going to decrement... Let me think. This could be... Hold on. I could be going backwards, because if you think about it, the row... Yeah, I think I'm doing this backwards because I'm going from bottom to top. So we want to keep incrementing, actually. We want to, if we're going up, we're incrementing. So row is less than, okay. What if, since we're already incrementing here, why do we have to start another loop that increments further? You know what I mean? But we also have to count for any other rows that might be matches. But if we find a match and we move everything down, we just set where we're currently on back to 1. Okay, let me write down this logic, because I think this would be a cool way to implement it. So we already know that we want to move every block down by 1. And we're already in a loop to where we can move everything down. So everything in the grid is going to be moved down, but if it finds another row that is a match while it's moving everything down, it just moves everything above it down as well. Right? So it's more like move every row down that is not a match. That is really what we're trying to do. Move every row down that is not a match. Every time you find a match, you don't have to move that row down. Well, I mean, you do move that row down, but it's gonna disappear. In the sense that everything above it will move down by 1. So we're moving every row down, and if we find another row... So let's reword that. Move every row down. If we find a row that is also a match, so because you can have 2 or 3 or 4 matches in one clear. So if we find another row that is a match as we're moving rows down, then the logic is to, because everything has to be moved down already. So we have to move them now twice as far down. So if we find a row that is also a match, increment the amount of rows we move it down by 1. So now we kind of have our logic here. We're going to keep track of how many rows we're deleting. So in here, we're going to say deletion rows. Deletion rows. Okay. It's not false. It's going to start at 0. And as we find rows that are matches, we're going to increment the amount of deletion rows by 1. So if all the blocks are active, deletion rows go up by 1. And then every row above us will start moving down as we continue to go through the loop. And every time we go through the loop, we're moving them down by a certain amount, and then we're checking that row to see what happens. So we don't delete on this iteration, we delete on the next iteration. I think a graphic would kind of help explain how this works too. So let me pull out a Google Sheets real quick, because this will be a little more easier to explain. It's a little complicated because as we're talking about, we realize, oh, we can make a very compact algorithm with this, but we have to understand what we're doing in order to not screw this up. So here, I'm just making an easy little grid system here. So for every, let me get borders going here so we can see everything. Okay. We do like gray actually. All right, so here we can see we've got a grid system, right? Let me just add a few more blocks that are highlighted or something. And then we'll use this to explain what our logic will be. So if we were to land a block and, like, let's say we landed a block here and it created this fill, right? Like we landed a block right here, so it created this fill. I'm just gonna highlight it like this. So now this row and this row should be considered clears, right? So let's start by going through what our algorithm will do. Starting at the bottom, because that's what we specified, starting at game grid 0. So this is 0 here. It's going, or row 0. It's going to look at every value here. That's what this loop does. And say, do all these match? If they do, or if one of them is not active, is all active is set to false. But if all of them are active, we know we have to get rid of this row. So we set deletion rows equal to 1. Right? That tells us how many rows we're going to move everything down by. So we go to the next row. We don't even do anything. We just go straight to the next row. And then we check, is deletion rows greater than 1? We don't even have to check that. We can just say, okay, move by the number of deletion rows. So we do that. Boom. It's now moved down, right? However, before we can do that, we have to check if it's a clear. So let me give you, let's just say this was a row that was cleared as well. So check if it's a clear. So if it's a clear, increase deletion rows, else we're going to actually do something. So let's say this was a clear 2, right? Deletion rows becomes 2. Now we go to the next row. Well, we know our deletion rows is 2. Check if it's a clear. It's not a clear, so this is our first row that's not a clear. Let me add a couple more rows so we can exemplify our example here. So anyways, we're on row 3. Well, deletion rows is 2, so we know we're going to move this down by 2. Now we're back up here. We already checked if this was a clear. It was not, so we move to the next row. Ah, look, another clear. Set deletions row up by 1. Don't do anything. Next row. Deletion rows is 3. This is not a cleared line, so move down by 3. 1, 2, 3. Check the next row. This row's not a clear. Deletion rows is 3. 1, 2, 3. Do some cleanup. Cause technically they're so that's what we had to do. Let me continue this. So we were here, right? So we go to the next row. Deletion rows is 3. Boom. That's the clear line. Deletion rows is 3. Deletion rows is 3, etc., etc. All the I could actually count it here. 1, 2, 3. 1, 2, 3. Boom. You can see that that is the algorithm that we have to utilize to do our clears properly in Tetris. So now that we figured out our algorithm, let's finish implementing it. So here we're incrementing deletion rows by 1. And so we said if it's not active, we need to move it down by the number of deletion rows we have accumulated. So in order to do that, we just loop through every one of these, every one of our columns. And we say game grid dot grid. We're gonna move it down to a different grid level. So grid, do I have this backwards? Let me think. No, I don't. I'm using X to represent the rows, and I'm using Y to represent the columns. Let me double check that I'm not doing this backwards, because I feel like I am. Because the more I think about it, the more I realize I think it's... I need to check if it's elements of 10 or rows of 20. Is it rows of 20 or rows of 10? We specify a set of 10 objects that have 20 instances each. So 10 instances. So yeah, these are the columns. That's what I was afraid of. So I just need to adjust this logic a little bit. And it's kind of confusing when you're doing for loops, right? To really understand what you're going for. So what I'm going to do is I'm going to refactor X to be called our column. That's our column index. And this represents our row. So this way we can see better, okay, this is what we're actually doing. So you can see that row and column are reversed right now, which is not what we want. We want to do every row, so we're going to have to reverse these two. And so I will undo the 2 refactorings here because now I know these are backwards. So we need to access GameGrid element 0.length. That way we're doing it 20 times because each grid element has 20 instances. So that's something you have to make sure of. Be very careful with your grid systems, your arrays. You can easily get messed up, and I almost did actually. So again, now this represents our rows, or our row index, and this represents our column index within the game grid, which you can see, excuse me, is more along the lines of what we want. So now we're going to go through each row, which is like this, and check every column, right? That's really what we're aiming for here. So I'm going to change this to column index, So for each row, check the column index in that row, and say, okay, we are going to shift them over. So row minus whatever deletion rows is at column index will now be equal to my current status, which is at row column index. Essentially shifting everything down by the number of deletion rows here. So I can refactor this to just say that, so that it doesn't look all weird. So just call this shift block down by number of deletion rows. Like that. So this whole thing here represents clearing lines. Well, this actually checks if we clear like full lines. Clear full rows. I guess we should call it check and clear full rows. Like that. Okay. So you can see here it keeps track of deletion rows by making it equal to this as it goes on. So the references will go in through deletion rows, it gets incremented, and it comes out, so that gets stored for the next iteration, so on and so forth. So this makes every block shift down. Now what about the other blocks? the new rows, right? So if everything shifts down, then the current rows will eventually, like, we'll get to here, right? So then we have like a bunch of blanks. What happens to all those is the question. If we take all these and shift them down, the old rows become blanks, right? Kind of like how when I did this operation, I cut them, so these all become blanks. So the final piece is to make them blank when we shift them over. So change the row and then set the old one dot active to false. And actually, we shouldn't be making them equal to each other because they're references. We should be setting their active values instead, like that. So with all that done, we now have line clearing. So we're going to attempt to see if we can actually clear lines now. However, making a setup for this with just random falling blocks is not going to work out for us. So we need to actually implement user input now. It would be nice if we could actually control our game, because it is a game, right? We want to accept user input. So I think now is the time to create our little graphical interface and make it so we can interact with our game a little. Usually you want to incorporate the graphical element at the same time as you incorporate the user input, because they're usually tightly tied together. But we have the basic backbone of our game. We can rotate blocks. We can't move blocks yet. Let's do that real quick. Let's make a function to move block right. And we'll make a function to move block left as well. So we'll reference, again, generic functions that we can use to represent directions. So we have rotation directions here. We're actually going to make another set of enums to represent move direction. And we'll just do something very similar to what we did for rotation direction. We're just going to be using left to represent a -1, because that means -1 in the Cartesian coordinate system, or right, which represents a 1. And again, we'll specify a constructor to indicate a value, which then we can access a little later by storing this value in here, like so. So left represents -1, right represents 1. Pretty much the same setup as our rotation direction was. So now we can do move block, but we can use move direction that we just created to represent which direction we want to move in. And now we just have to make the move block function. Okay, so inside the move block function, it's as simple as moving the player's position, right? Wrong. We have to actually check for collisions, as we always do. So we kind of already did that. This is our check for collision setup, basically. We don't have to do the rotation part, we just have to do this part. Here. So this will get all the points we need to check in our grid system. We're going to use our current piece. So we're going to say get current piece, I think. Oh, get current shape. That's what we called it, I believe. And now that we have our points, we need to check them within the grid. So I think most of the time, let me see. Is occupied. That's what we need to check. So we need to make a for loop with is occupied and return if there's a collision. So you can see here I'm about to copy paste this. We can make this more generic as well by returning the amount. It's just this part is kind of specific. So we already have an is occupied, which is good enough for us to actually check. We just have to compare it to our points. So we're going to go through all of our points and see if is occupied. And our offset is going to be 0. We're just going to check whatever points we provide here. So if is occupied, then we can't move because, well, one of these blocks is... Oh wait, we are offsetting this by the movement direction. My bad. This is where we specify our direction, not value. So if the position we're moving to is occupied, we can't move. Boolean is no collision, is free, is true. We'll assume it's free, but if there's a collision, free becomes false, and we can break out of this loop because we don't have to check the rest then. If not is free, or excuse me, if is free, then we're allowed to move. So that's when we actually move. So if is free, move. So to move, we just have to change our position. So position.translate equal to whatever our direction value is. We don't move up or down, just left or right. So there we go. Now we can call move block right and move block left. We don't want move block to be public. We want that to be private. It's only available internally inside of here to be used by our public functions. Function scoping is a good idea because as you refactor and you build more of these small functions, you don't want your main functions you want to be using to be called from these little functions, because then you'll get confused with which functions you should actually be using. So again, I would want to be using rotate clockwise and rotate counterclockwise, so I really don't want to be using the rotate if space is free function, which you can see actually already defaulted to private. So same with the rotate piece function. I don't want to be using that publicly as well. So we want to try to keep our variable or function scopes as much as possible. It's a good idea to keep all of your public functions together and separate from your private functions, because your private functions aren't accessible in other places. So when you look at it, you usually don't want to see like your public functions or your private functions, as these are not accessible outside of just being utility functions for your public functions, which generally should be small. Yeah. In any case, we now have a way to move the block left and move block right. We can try this out real quick, make sure it does indeed work, and make sure that we can move to like the edge of the field. So instead of doing this on a timer, we're gonna do move block right. You can see when I do move block isn't there now. It's not accessible outside of its internal class, which is exactly what we want. So you can see it moved all the way to the right edge, and then it doesn't move any further. That's as far as it can move. So, oh, we got an array out of bounds. Check and clear full rows. So we got to see it fail, actually. Out of bounds exception 10. I'm not sure why it would check 10, so let's have a quick look there. We're checking every column. Column is 0, column is less than gamegrid.grid.length. The problem is, I don't think this says what it should be saying. Because the column... Let's look up here, actually. So each element of these has 20 values. So that would be for row, which gets filled in here. Ah, so these are actually backwards. Columns are represented in the first one, while rows are represented in the second one. Which column we're on versus which row. The row is is up and down. So yeah, these are a little backwards. It's kind of hard to think about these when it's like this, because we iterate through each column. There's only 10 columns, but we want to be doing each row like one at a time. So the logic, the logic is a little backwards and weird. So this would actually be... So I think I'm gonna have to adjust all these because, hold on. Does this not have the column? Oh wait. So which row we're on is determined by the second value. So which column are we on? We're just going through all of the columns, right? So we need to do gamegrid.grid.length, which is every single column. We're going to do every single value in that column. Yes, that's what we're looking for. So every column, which there are 10 of, excuse me. 10 columns, yes. So I'm gonna have to flip all these. But there are 20 rows. But I have to iterate through all the... I'd iterate through all the columns to delete the row value that is... Yeah. Gosh, it's so hard to sometimes, like, wrap your head around it. So, the row is actually stored here. So we can think of each array as one of these, right? That's what each of the array elements is it's storing a column. So what we have to do is we have to iterate through all the columns and check the row that we're currently on. So that's this value here. And then we have to subtract by the amount of deletion rows we have. So I believe this won't error out anymore because now we have the proper setup for that. Not 100% on that, but that's why we're gonna have to test the line clearing. You can see the block actually disappeared, so it must have thought that this was a clear. So we're gonna have to fix that. So if any of these are not active, is all active is false. So if it is all active is true, otherwise, we have to shift block down by number of deletion rows. Well, the number of deletion rows should be equal to 0 when there's no line clears, right? Because everything has to be active. So the deletion row count shouldn't be increasing right now, because is all active should be set to false the moment there is not one of these active grid squares. So we're iterating through all of our rows to see if that is indeed the case. Oh, I see. Right now we're iterating through not these, but these. So this is where things get a little tricky, right? Because we're doing column right now, as in like these values here, which is not right at all. We need to be checking everything here, so we have to iterate through all the rows actually. So it's better not to use the word column, but probably to use the name X to represent this, because it's really the X we're checking, right? We want to check across, so to check across along the X, you have to move, you have to change this guy. And this guy has to increment based on how many of those there are, which this is actually doing right now, so that's good. And then which row we're on has already been determined by row. Isn't that the same logic we just had, though? Let me double check that. Comma 0, comma... Yeah, it is. So this is, in theory, the correct logic. But we can, let's output this. We can see this visually for ourselves. Make sure we're doing the right thing here. X. So by outputting all those, we'll be able to kind of see what is going on here when we actually snap things. So let's go ahead and run that. It's only going to output when the block lands, because that's when this gets checked. So after one landing, we'll see. Okay, so we kind of saw it outputted. I need to find it. Okay. That's right. Clearly just missed it. Okay. So it's right here. So we can see each of these outputs a list of blocks. And I need to, well, I guess I could comma separate it. Yeah. So we can see each array returns 20 values. That is 20 values. So what that means is that this is it's iterated through 10 times, so we are indeed doing each column here. So we have to check the last value, or the row in this case, for each column. So I wish we could return a more user-friendly version of this, so let's do that real quick. All we have to do is return whether or not it's active or inactive. In order to change what is outputted by the system out print line, you just have to override the toString function to give a different value. This is called function overriding. So we have to specify a value here. So we're going to return whether or not it's active as a number, or we can return it as a symbol even. So return active, and if it's active, we're going to return, we're using a ternary operator here. If it's active, we're going to return an O, otherwise we return an X. And this way we kind of get a better idea of whether or not a block is active or not. We can also include the color, but we don't really have to worry about that right now. Anyways, we'll let this run again. See it one more time. Okay. So somewhere nearby we should have a grid. Alright, so we can see here that all of these are X's, which is, I don't think, what we want. Okay. So that's when this is called check and clear full rows. So clearly this is not giving what we want. But let's think about this for a second. If it's only showing X's everywhere, then none of these are considered active, so of course it's going to clear all the rows. So maybe my logic is wrong. Maybe we're just not grabbing the right data. So since we're not grabbing the right data, we're going to have to figure out how to grab the right data. Because apparently it doesn't give us what we want here, as we can see from all the X's. We're expecting some O's set down here, which should be like up here or something is ideally where it would be. Either that or it's actually in here, like 1, 2, 3, 4, I think. Actually, I'm noticing something. Isn't this 20 values? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is 20 values of 20 values. So we're literally iterating through the same, we're iterating through rows to get every row. Okay. So that is not what we want. So we kind of messed up in that regard. We want to select all the columns. So to select all the columns, we need to select the row we're currently on, which will give us, or excuse me, we need to select the row we're currently on, not the column. So yeah, it makes sense that this will return 20 elements. So to get the 10 elements in a column, we need to iterate through... We know it's going to be 10, right? Like, we know we have to iterate through this many elements to figure out if the row is satisfactory. What value we substitute here? It should be the row number, because the row number... So we have to iterate through all these, is what we have to do. Each of the first values, or each of the values inside of here, is going to remain persistent, which we're kind of doing here, but we're getting the row. So I think we're supposed to get the column here, but we're not really returning the columns, are we? Because this is the columns are in X. So X has to be adjusted. Row has to just be remain persistent. Because each value in row like if this is a 10 by 20, right? Then let's say we're on row 0. Well, all 20 values along that grid are in row 0. No, that's not right. We want to get all these, so this should be the dynamic value, right? If this stays like equal to 0, then this will represent like 20 values like this, and we keep it the same, like 0 going across. Like let's say this was 0 actually, but it's really this is 0, so this will represent 0, 0. This block right here represents 1, 0, 2, 0, and so on and so forth. So it literally is like an X and Y coordinate system. So it's just a matter of fixing these loops to incorporate that, because this actually does mean the X position within the grid, and it's going to go up to 10, and we know it's going to go up to 10. The length of these guys is 10. So if you specify it like this, then you get your 10 loops. So then you have to choose the right array elements to loop through. So, again, we're incrementing this value and keeping this value the same with each iteration. So change this, keep this the same, right? So what's confusing is I think we got, when we output this, we got like 20 values here, right? Which makes sense, but really what we should be outputting is every one of these. And that'll give us what we're truly testing for. So how about we do it this way? We'll output a line at the bottom, and we'll just output each individual one. I think that'll give us the accurate results we're looking for. Okay. Let's see. I think we were just outputting them wrong, but we had the right, like, algorithm. Which doesn't explain why they, like, all still disappear. But, you know, we'll get to that point. So I only outputted one. Interesting. So the reason why it cleared is probably because we went through one, but we didn't go through all of them. We have to go through every single row to check for deletion rows. We start at the bottom. So this is going to represent Y, right? Let me change this back to Y so that we kind of understand this better. Refactor that to Y. Okay. And that way we just kind of understand it a little better than before. So we are going through every Y per for loop. And when we're checking all of these, we're checking one row, right? Yeah, so we're checking one row. You know what? I think we're starting on the wrong side, because look, this returned all X's. So it wouldn't have been the bottom row. It would have been probably the top row, is my guess. So is the grid backwards then? Is the question. I think the bottom though is 0. From what I can tell. Let me double check though what we outputted for the grid. Because if you look where I draw the... Where's the draw board function? I literally had it. Draw board. Here it is. So yeah, we start and we go backwards, right? So we're always outputting from the top to the bottom. So the bottom row, which is gonna be this X position, or the Y position, excuse me. The Y position is gonna be 0 last. That's the last row that's outputted, all the zeros. So if we were to access them in here, we're starting at 0 and working our way up, which makes sense to me. The question is, why didn't the rest of them appear? That's the real question. Because we should have gone 20 lines of this, not just one line of this. What happened to the rest? That must be our problem, right there. Part of our problem, I would say, because the other problem is we're not getting the correct results we're looking for. Let's make sure our output function is right. I mean, it should be. We're outputting either an O if it's active, or an X if it's not active. And we're making sure we're setting active when we draw the grid, because the grid literally is determined by whether or not there's an O or an X, or active and inactive. So I'd imagine we're doing the right thing here. So yeah, we can see this. In fact, now if I just output this, we won't get dashes, but we will get X's or O's. So we can clearly see that they are all X's at first, and they will turn into O's eventually. So we know for a fact that... Oh. Maybe not. Hold on. Something's not right. Oh, wait. I think that's conflicting with our, clear lines that have full rows function. Let me comment that out real quick, because I want to just make sure that indeed it is showing O's when these are cleared, or when these snap. So yeah, we can see O's do appear when they snap, so that's good and all. I'm gonna turn these into dashes though. The X's are kind of annoying. Alright, so we're back in here again. Yeah, let's try to get this figured out real quick. What is going on? I probably misplaced like a column index or something when I was deleting stuff. Like, I'm more concerned about this down here, where every, let me think. We're moving we're checking every column, right? So that's gonna be an X. I'm gonna put X2 here to understand that is indeed an X. Actually, we can use X here. But that does represent X. Shift block down by number of deletion rows. This represents X, so I'm gonna put X here, and I'm gonna change row to Y. We now understand that X represents the X part of the, yeah, so we can see we already fixed that down here. We identified that part. So I wasn't too worried about that. What I was more concerned with was why are they all considered inactive, even though there should be some active squares? In theory, there should be some active squares. Like, we shouldn't be shifting down, because the number of deletion rows should be 0, right? And why my deletion rows will still equal the same value. So just setting it to itself. Oh, wait. Setting it to itself. Aha. We only delete if there's rows to delete. That is our issue right now. I didn't even think about that. If deletion rows. So basically, here's what was happening. Every time we tried to delete a row, is greater than 0. Well, we would shift everything down, but if the amount of deletion rows was 0, right? Which it was. We just set it to itself, basically. And then we set its active value to false. So we were basically just setting every value to false. Whoops. Just missed on that little detail there. Everything else is good though. So here it's not considering them as cleared anymore. And we can actually see the clear checks now properly. We should. So let me scroll up a little bit. What's weird is it's only showing one set of rows again. I'm not quite certain why. It should be showing more. Because it's supposed to show for every row iteration. So that part I'm not sure of. That might be an issue, actually. That's what I was more concerned with. I was concerned with why we weren't getting more outputs. Because we're supposed to. We're supposed to get one of these calls for every single iteration of this. But we're not. At least I don't think we are. Because GameGrid.length is definitely 10. Or excuse me, Yeah, it's 10. And game grid, each element is definitely 20. So why this doesn't show more is a little confusing. And worrisome. It could be something to do with print line though, or it could be something to do with me flushing the input all the time. That could also be it. Let me go back to the draw board real quick, because I think I had that before, like clear screen. Maybe I didn't, I don't know. Hard to say directly, but all we know is that new line should be outputting a new line, so we would expect it to. But this is just the new lines from the clear screen, not the new lines from, well, the rest of these functions, which should be calling. Maybe we should confirm that this is indeed running every single time? Probably. I mean, it should be. It's in a dang for loop. Like, why wouldn't it be? Yeah, I think I saw stuff, so. There it is. Pod 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So on and so forth. I think I know what's happening. I did forget that this was in a thread, right? So, because it's in a thread, if the amount of time it takes for it to render all these is greater than the amount of time it takes for the next cycle to happen, it's not going to render everything. It's just going to go to the next cycle. That is going to be my educated guess here, is that these for loops don't finish before the next cycle, so all these system outs don't actually occur. Theory. Instead, all we get is we get some of it. Or we get them even out of order, it seems. There's a dash here. There's dashes. And then it just straight up jumps into the next thing. Oh, I see what I did. I also did this. I did a print line for every single one, when I really should do it after all these output, right? That could also be it. I'm just printing like a bajillion lines that I don't need to print. All good theories. So yeah, you can see now it's doing all this. Ah, and then we break because it found a dash. Yes, so that is behaving the way it's supposed to. Once it finds a dash, it breaks out. So all of these were dashes. It found one dash, called out. Dash, called out. So I bet you if I do move left, we'll get 2 instances where a couple of blocks will actually be checked now. So let's try move left. Everything's working. It's amazing. I figured we were just gonna run to some debug. So I think the first row is not gonna be detected because there's a dash, but the second row should have 2 O's before it detects. So let's go back up here. All right. So you can see here, dash, and then it found 2 here, OO, and then a dash, and then realized, okay, well, we don't have to go any further then. Once it's an entire match, it will do the rest of the code. So here's what I want to test. One final thing I want to test is instead of every block being inactive at the start, I want to make every block active at the start and see what happens. Well, maybe not every block. Maybe every, like, Maybe the first like 10 rows or something. I don't know. We're just gonna write some code to quickly do that and see what happens. So our game grid should already be initialized at this point in time. So we will do if I is greater than 10. Oh, let's actually do it right here. False. I is greater than 10. Then say less than 10, excuse me. We want the bottom filled. So now these blocks will fall. Oh god. Hold on. I is less than 10. Let me think. How about J is less than 10? Let's do that. That's what I want. There we go. So all these should clear, in theory. Hey, would you look at that? It worked. So all those full lines got cleared like immediately. Let me scroll up a little bit. I think I got rid of the output already though. The test output that we had earlier. Oh, no, I didn't. So you can see here, it found some full rows, and then the next row it didn't, and then it moved everything down. So that's perfect. That's exactly what we want. So there we go. All of our functionality we need for a Tetris clone is like ready to go now. We have rotating blocks, we have moving blocks, we have clearing the field. So that's all the requirements. Tomorrow we'll implement the game rules, we'll implement the GUI, and we'll implement player input. But we have all the raw functions ready to go. The game is ready to be played. We just need to make the game now. All the raw implementations there. Anyways, that is it for today's coding session. I don't think we went too far over today. Fred, we did. We went way over. Last time I went an hour 30 over. This time I went an hour 40 over. So, or excuse me, 40 minutes over. It's getting worse. We're having a good time. So, we did a lot of debugging. And that's because I failed to realize that we literally stopped. I forgot about the whole break part. So let me fix this. We don't want the bottom 10 to be set to true anymore. Let me remove some debug stuff, and then I will commit this. It's always good to commit. Keep like a history of what you've done. Anyways, for those of you that tuned in today, hope you enjoyed. I'm actually gonna do some other stuff, but we're done with the programming session for today. Implement all Tetris basic functions. Yeah, that's all the main functions that the game needs in